Hello everyone. Today we're going to start on 3.6, which is called Eigenvalues and Eigenvector. So this is probably one of the more important section in 3.6. Well, technically speaking, the entire chapter 3 is very important because they have a lot of different concepts that is required for you to understand what's going on. But eigenvalue is even more important because it's going to be one of the major way for us to solve differential equation using it. So let's try to define what eigenvalue is. So let's start with the following. Let's say given a linear function, or if you want to think of it as a linear operator. Let's say this linear function L, oops, maybe I don't need this right here, L that map from some vector space back to itself. Now normally when we define a linear function, there's really no good way to actually define it other than whatever we use to define L. But for some special vectors, it might actually be true that we can actually define L of that vector in the following way. So it doesn't happen all the time. It only happens for some special vector. For some special vectors, let's say vector u, it is possible, it may happen that vector u and the output of vector u for the linear function L are basically scalar multiples. Meaning that L of vector u is just equal to some value, some constant times vector u. And this symbol is called the lambda symbol. If this is true, if the vector u is not the zero vector automatically satisfies this condition, pretty much. Because a linear function, when you plug in 0, you usually get 0 as one of the results. And so it's automatically equal to any constant times 0 vector. So if vector u equal to 0, and it satisfies the equation L of vector u equal to lambda vector u, then vector u is called the eigenvector of L. And the number lambda is called the eigenvalue of L. Now, however, the eigenvalue is unique to the eigenvector, so they have to pair up. So the eigenvalue of L with vector u. Now, the term eigen is actually, I believe, is German. So there's another word for that. An eigenvalue, or an eigenvector, let's start with eigenvector. An eigenvector is also called a characteristic vector. However, you won't see me call that. We usually just call it eigenvector. But it's also called characteristic because the word eigen actually means characteristic. That's why. And eigenvalue, and yes, you can guess it. The eigenvalue is also called a characteristic value. And so in here, the word eigenvector and eigenvalue, because the term eigen means characteristic, therefore it kind of indicates that these value and these vector are somehow a special characteristic of the linear function. Okay, and it is true. It's actually have a lot of things to do with the linear function, and it's a very special property of the linear function that allow us to actually exploit the in a way to use it to solve other things. Now, one thing I do want to point out is the following. Look, since L is linear, any multiple of vector u will have the same exact eigenvalue. Remember, eigenvalue and eigenvector go together. For a specific eigenvector, there is a specific eigenvalue for that. And for a specific eigenvalue, there usually a family of specific eigenvector that will do that. So since L is linear, any multiple of vector u will have the same exact eigenvalue. So meaning eigenvalue are pretty unique, but then the eigenvector that go with a specific eigenvalue can actually be any multiple. Imagine the following. Let's say we let u be an eigenvector with an eigenvalue lambda. So therefore imply that L of vector u is equal to lambda times vector u. Now let's say if vector v is equal to some constant times vector u, some kind of multiple vector u, then what we know is the following. Then if I take L of v, that means it's L of c times vector u. And since L is linear, the constant c will move out of the linear function. And then we already know what L of u is, because u is an eigenvector. Therefore, I can say L of u would just be lambda u. And now if I simply rearrange this, that will mean it's lambda times c vector u. That will mean it's lambda times v. Therefore, show that vector v is an eigenvector also, and it has the same exact eigenvalue, which is lambda in this case. Another important thing about eigenvector is the following. The vector 0, the 0 vector, is never called an eigenvector because it actually always works. So therefore, it yields no significant meanings. In a sense, it is a trivial eigenvector. So therefore, we don't consider it to be an eigenvector at all. Now, however, the scalar 0 can be an eigenvalue. It's called an eigenvalue only if this is true. Only if L of vector u is equal to 0 times vector u, which is equal to 0 vector, for some non-zero vector u. So therefore, you can use 0 as an eigenvalue as long as the eigenvector that go with 0 is not the 0 vector. Because once again, the 0 vector will always work. All right. So now how about we try to figure out how to, or how about we start with the following first? How about we just try to see how eigenvalue and eigenvector work? So let's try this example. Very simple, just to illustrate the concept a little bit. Let's say we have a function L. Let L map from R2 to R2. And I'm going to define what F is, what L is. Defined by the formula L of vector x, which is equal to L of xy, is equal to 1141 times xy. Let's say given that L has 2 eigenvector. Let's say it's 1, 2, and 1, negative 2. Now, we haven't figured out how to find the eigenvector yet. So let's assume that I gave you that. I do want you to try to figure out how to find their corresponding eigenvalue. Remember, every eigenvector must have a corresponding eigenvalue. to go with it. Okay, because that eigenvalue is what the scalar is that define the multiple. So how do we go about solving for the eigenvector, eigenvalue, now that we know the eigenvector? Well, let's try to figure it out. So let's say we're going to go ahead and define this. We normally like to use the vector u to indicate eigenvector and lambda to indicate eigenvalue. So you'll see me use that a lot. Unless I cannot use the letter u, I will almost always use letter u to represent eigenvector, just so they be a little more consistent and easier to follow the math when you keep doing that way. So I'm going to call vector u1, so the subscript to indicate different eigenvector of the same function. Let's say vector u1 is the eigenvector 1, 2. How do I find the corresponding lambda? Which I'm going to call, of course, I'm going to call it lambda 1. Well, let's go for it. So it's simple. So the idea is that L of vector u1 should equal to lambda 1 times vector u1. So therefore, indicate that L of 1, 2 would equal to some constant lambda 1 times 1, 2. So that seems simple enough. All I have to do is just apply L to 1, 2 and see what happens. So it's 1, 4, 1, 1 multiplied by 1, 2 is equal to lambda 1 times 1, 2. Yes, I do have to write the vector 1, 2 vertically in order for the equation to make sense in this once I put in the matrix and multiply. So the left side, the right side is pretty simple. The right side would just be, actually I'm going to just leave it lambda 1 times 1, 2. And I'm going to go this side. So 1, 1 times 1, 2 would be 1 plus 2, which is 3. 4, 1 times 1, 2 would be 4 plus 2, which is 6. So it's simply clear to me that lambda 1 must be 3. So therefore, we find out that the eigenvector, eigenvector vector u1 equal to 1, 2 has a corresponding eigenvalue lambda 1 equal to 3. Now you can definitely go ahead and try to find the eigenvalue for the other eigenvector. So I'm going to call vector u2 to be the eigenvector 1, negative 2. And go ahead and find lambda 2. So I'm going to ask you to, if you want to try that out yourself, pause the video so you can not watch and just do your own math, but I'm going to continue. So if you don't want to see the answer, then just pause the video and just do your work. So that would mean is 1, 1, 4, 1 multiplied by 1, negative 2 should equal to the lambda 2 times 1, negative 2. So let's go through this. 1, 1 times 1, negative 2 would actually give you negative 1. 4, 1 times 1, negative 2 would actually give you positive 2. So it seems to me that lambda 2 must equal to negative 1. Therefore, we find the two corresponding eigenvalue. Pretty simple. Now, before I show you how to find the eigenvalue and eigenvector, I do want to talk about one very important application of it, and also kind of show you why it is powerful application. Is to use the eigenvector as basis. So we just talked about coordinate basis and we learned how powerful that is. If you can form a basis for a vector space or subspace, then you can pretty much allow any kind of linear function and turn it into, rewrite the linear function into a function of the coordinate vector, and therefore essentially allow you to turn almost whatever vector space that you are working with into a Rn space. And therefore make it a lot easier for you to do a lot of the math and also even visualize or think about how to describe it. So therefore, one very useful application of eigenvector and eigenvalue is to use them to form a basis for a vector space. And of course, you might be thinking that, well, so that we can just simply form a basis. We can only form basis for Rn. Am I right? Well, eventually we're going to talk about eigenvalue and eigenvector of other vectors, other linear function, like the differential operator. That's what we're going to talk about later on. And I'll show you how that works later on when we get to it. But we're definitely not limiting to just the Rn space, even though very likely that would be the case, because we will kind of need some kind of matrix to form the eigenvalue, eigenvector. But we'll eventually get to use this concept on operators that are not on Rn. And you'll see how all that works out later on. So imagine the following. Let's say we go define some kind of vector space. Let's say V. Let's say we go define this first. Okay, let's define a function L to go from V to V. And let's say, and let's say L is linear and it has eigenvector. Let's say vector u1, vector u2, to vector u sub k with eigenvalue. Let's say lambda 1, lambda 2, to lambda k. So therefore implies the following, that L of vector u1 would equal to lambda 1 times vector u1. L of vector u2 would equal to lambda 2 times vector u2. And this process go on to L of vector u sub k, and that's equal to lambda k times vector u sub k. Now, imagine the following. Let's say, just so happen, let's say V is k-dimensional. K-dimensional. And therefore implying that a basis must have k, that many vectors in it. And how about the following? And vector u1, vector u2, to vector uk, all the eigenvectors, are linearly independent. So now, if you think back at what we learned in 3.5, we have a theorem that states that if you have a n-dimensional vector space, and you can find n that many linear independent vector in it, then this group of n vectors automatically form a basis. So therefore, that's what we were hoping for. That's what I'm describing in this scenario. We have vector V, we have vector space V is k-dimensional, require k linearly independent vector to form its basis. And just so happen the eigenvectors are all linear independent, and also we have k that many of them. If that's the case, what we know is the following. Then this set of vectors will form a basis for V. Therefore implying the following. Therefore imply that if vector V is in V, then vector v is basically equal to some linear combination of vector u1 to uk. So I'm going to call it c1 vector u1 plus c2 vector u2 plus dot 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 plus ck vector uk. And of course, in this scenario right here, you can think of as c1, c2 dot 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 to c sub k is basically the coordinate vector of vector v. Now, what's interesting about this? Well, what's interesting about this is the following. Now, what happens if I want to evaluate? What if I want to evaluate the function L by plugging vector v? What would happen? Well, this is basically what happened. Let's say I want to now evaluate L of vector v. Well, because vector v can be listed as a linear combination of the eigenvector, I can say that's the same thing as L of c1 vector u1 plus c2 vector u2 plus dot 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 plus c sub k vector uk. Now, but because L is a linear operation, or a linear operator, or linear function, I can now separate this into L of c1 vector u1 plus L of c2 vector u2 plus dot 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 plus L of ck vector uk. And next thing I also want to do is pull out the constant c. So therefore becomes c1L of vector u1 plus c2L of vector u2 plus dot 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 plus c sub k L of vector u sub k. Now here comes the important part of the beauty of using the eigenvector as the basis. Because now I can actually evaluate what L of u1, L of u2, all the way to L of uk relatively easy. Because u1, u2 to uk are all eigenvector of L. And therefore, property of eigenvector of L is that when I plug it into L, it just becomes multiple. So therefore, this first one just becomes c1 lambda 1 vector u1 plus c2 lambda 2 vector u2 plus dot 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 plus c sub k lambda k u vector u sub k. So therefore, it has the effect of just simply multiply each of the term in this linear combination by the corresponding eigenvector, eigenvalue. So you can see that vector v is this, and then L of vector v, which is right here, just have the effect of multiply the first term by the first eigenvalue, the second term by the second eigenvalue, all the way down to the last term, the kth term, and multiply that by the eigenvalue lambda sub k. Now, that is definitely something interesting, but even more interesting is if I now want to simply form a way to define this linear operation in matrix form. Then the matrix form actually becomes this right here. Imagine the following. Because remember, we have the coordinate vector also. So in this case, if let's say vector v, if vector v is equal to c1 u1 plus c2 u2 plus dot 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 plus c sub k vector u sub k, then we basically have the coordinate vector c1, c2 dot 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 to c sub k. And now I can actually define a matrix that will allow me to identify the proper coefficient for the output. So if I think about it, if you just look at this right here, so this, okay? So v has a coefficient, coordinate vector this, then what is the coordinate vector of L of vector v? Well, Let's write it out. And I'll show you how we can form that. So the coordinate vector for L of vector v is actually c1 lambda 1, c2 lambda 2, dot 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 to c sub k lambda sub k. So now the question is, can I now notice what we're doing is basically 3.5.4, theorem 3.5.4. I'm going now, instead of working with the vector v and try to identify L of vector v, I'm now going to try to find a way to define this function L by relating their coordinate vector. So how do I do that? So this is how. If you think about it, this is basically what happened. Let's say I want to do L of vector v. That would actually transform into, I'm going to need a different function. So I guess the next level after L is m. So I'm going to say m of the coordinate vector of v. So this is the coordinate vector of vector v. And now I can actually define this into a matrix form, because all I'm trying to do is multiply each of these numbers by the corresponding lambda. And to do that in a matrix form, it actually requires a very basic matrix called diagonal matrix. This matrix is called diagonal matrix because they only have a diagonal. The only number that appear on inside this matrix are along the main diagonal, and everywhere else is just 0. And this diagonal matrix is actually going to be a k by k square matrix. And if I take this matrix and multiply by c1, c2, dot dot dot, c sub k, then what I have would be this vector. Maybe I should write, actually it doesn't matter, I can say lambda 1 c1, but actually, you know what, I'm going to write it the same way as what we see on top. That would now become c1 lambda 1, c2 lambda 2, dot 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 2, c sub k lambda k. And now this is the coordinate vector of L of vector v, the output. And so now to form this proper answer, now that we have the coordinate vector, I can now say, well, that just becomes c1 lambda 1 times the first vector in the basis, which is u1, plus c2 lambda 2 times vector 2, plus dot dot dot, plus c sub k lambda k vector u sub k. So it becomes very easy to evaluate a linear function if we simply use the eigenvector as the basis, because it basically simplifies any kind of linear function into just this diagonal matrix. But of course, that would mean that you have to identify the coordinate vector first. Okay, that will require a little bit of work to do, but it's not by all means any difficult things to do. So once you form the coordinate vector of your input, you can simply just multiply all the coordinates by the corresponding eigenvalue, which is symbolized by this diagonal matrix, to form the output coordinate vector. And then you can then use that with the basis to form your answer. Alright, unfortunately the video is already 29 minutes, so I'm going to stop right here, and tomorrow's video we'll talk about an example to show you how that works. Alright, I'll talk to you guys later. Bye bye.